I have the integral x squared over square root of 9 minus x squared dx. So I'm going to refer back to my notes from 7.3, and remember this table right here, this very useful table, be good something to have on your note card, is when you see square root of a squared minus x squared, use this substitution, and all your 1 minus sine squareds becomes cosine squareds. If you have a squared plus x squared, use this substitution, all your 1 plus tangent squared becomes secant squareds. And you have square root of x squared minus a squared, do a secant theta, and then all your secant squared minus 1s become tangent squareds. So on 3a, the one that I just had on there, what's the substitution? It's the first one. And a in this case is 3. So let's let x equal a sine theta. And I'm going to replace that a with 3. Okay, let's see, what do we need to know? We need to know how to simplify this. So consider square root of 9 minus x squared. With this substitution becomes the square root of 9 minus 9 sine squared. Okay, which is now 3 cosine, right? Well, all I'm really doing is figuring out what to do with this denominator. Numerator is easy. I'm just going to plug in 3 sine theta in there.
So you got the x equals 3 sine theta off of your chart?
Yes. I just remember when I have square root of a squared minus x squared, use x equals a sine theta. If you have square root of x squared minus a squared, I think it's x equals a secant theta. And if you have square root of x squared plus a squared, use x equals a tangent theta. That's the trig substitution cheat sheet. Now, if I plug in what I've got here, let's see. Well, first of all, I need to know what's dx. Right? Because I know how to replace this now. I'll know how to replace this, and then how do I replace that? Well, I got to find dx. And that's just the matter of taking the derivative. Derivative sine is cosine. So 3 cosine theta d theta. So this is that kind of reverse substitution. What you do is you just plug in directly for x. You're not trying to manipulate the integrand into anything. You just do a direct substitution. So on top, x is 3 sine theta, so that's squared. On bottom, I know I have 3 cosine theta, right? That's from over here. Right, and that's what square root of 9 minus x squared turned out to be. And then dx is You'll see the 3 cosine, 3 cosine. They do. So it becomes the integral of 9 sine squared theta. Just squaring both of them. 3 squared sine squared d theta. Okay, now we can do this one of two ways. We've now got an integral that I think we should be able to take. You can apply the techniques from the previous section, which is when you have even powers of sine, use the half angle formula we were talking about before. There's a formula, it's a substitute in there. Right, that's the sine squared, this is an identity from a table. Sine squared of theta. This is actually on your reference page. Sine squared equals, it's the half angle formula at the bottom of page 2. It's 1/2 times 1 minus cosine of 2 theta. That's reference page 2. So I could replace sine squared with this, and then that's actually fairly easy to integrate. But I'm also perfectly fine with you looking at number 63 on page 9. Is that helpful?
Yes.
So, if you have 63 sitting in front of you, what can I say that integral is?
1/2 u.
What's
So it's just that sine.
no you? I mean, it's just
Theta.
ignore the 9 for a second, right? It's just 1/2. Instead of u, it's theta minus 1/4 sine of 2 theta plus c. Or 9/2 theta minus 9/4 sine of 2 theta plus c. But we're not done. Why are we not done?
Because of the second third thing. To go back to
Right.
X's.
We're not in X's. If you look at the original problem, we were looking for the antiderivative in X's. So you solve this for theta, right? I didn't do that up front like I did in class, but you can do that here. Right, so that's x over 3 equals sine theta, or theta is inverse sine of x over 3. So that gets me this one. What do I do with this guy? Yeah, I mean, that's okay. What you should do is use an identity. Look on your trig sheet there and tell me, is there anything I can replace sine of 2 theta with?
Oh, that, never mind, I'm thinking.
Yeah, it's not sine squared, it's sine of 2 theta. So go look on reference page 2 and see if you see a sine of 2 theta.
Two sine.
So 2 sine theta cosine theta. And now that it's not a double angle, you use that triangle. Remember what triangle I'm talking about? From here, if this is theta, yeah, this is the double angle formula right here. So I'm going to have 9 halves theta minus 9 fourths times 2 sine theta cosine theta plus c. And that way I can use this triangle for theta. What triangle am I talking about? If sine of theta is x over 3, sine is opposite over hypotenuse, so x over 3, which makes this one 9 minus x squared, which is exactly the thing we've seen before. Okay, so plug everything in that we now know. 9 halves sine inverse of x over 3, that's the theta, minus 9 fourths times 2 is 9 halves. What's sine of theta on this triangle? X over 3. And what's cosine of theta? So cosine is adjacent over hypotenuse. Remember, so opposite over, or sorry, adjacent over hypotenuse, which makes this 9 minus x squared over the 3 plus c. And now we just simplify a little bit. This 3 times this 3 is 9, which cancels with this 9 up here. So I have a minus x over 2 square root of 9 minus x squared plus c. Well, I saw that I had 3 times 3 on bottom, which is 9, and I had a 9 on top, so 9 over 9 cancels. Still got an x and a square root of 9 minus x squared up top, and I got still 2 on bottom.
So anytime you go to the double angle formula, you draw the right.
Well, actually, it wasn't because I used the double angle formula. It was because I had a trig function of theta in there. I still had a sine or a cosine or a tangent. Anytime you have any trig function of theta left in there, draw the triangle. Because then from the triangle and from SOHCAHTOA, you can figure out what it is in terms of x. If this had been like a tangent of theta for some reason, then I would have done x over square root of 9 minus x squared. Opposite over adjacent. If it had been secant in my resulting formula here, I would have done secant is 1 over cosine, so it'd be 3 over square root of 9 minus x squared. You just use whatever trig function is appropriate. In our case, we had sine, and the reason why I had to use this is because you can't tell by looking at this triangle what the sine of 2 theta is, because there's no 2 theta in here. But if I use the double angle identity, now I can do it in terms of sine of theta and cosine of theta. You want your trig functions back in terms of just theta. That's why I had to do that. But yeah, you should, I mean, most of the time you're going to have to draw the triangle. And the triangle always goes back to what you used as your substitution. So just as kind of a a guideline. If you had, say you'd done x is equal to a secant of theta, if that was the substitution that was suggested, you can draw a triangle from that immediately, right? Because that is secant of theta is x over a. And secant is hypotenuse over adjacent. So I put x on the hypotenuse, a on the adjacent, and now this becomes square root of x squared minus a squared. Now I can do any of the 6 trig functions for that theta from that triangle. If I had x is equal to a tangent of theta, then you have tangent of theta is x over a, and you can draw the triangle for that. Right? Because this is opposite over adjacent. So x over a, and that makes this square root of x squared plus a squared. And I'm finding these, in case you don't see that, just by the Pythagorean theorem. But now, again, from this, you can rewrite any trig function from theta in terms of x. So, you know how much I love trig substitution. I've told you over and over again. I don't, but you've got to learn it. It's like every other Cal 2 student in history. Because it can be done, and it's what I would suggest to you is if you can do these 3, you'll be able to do the one that I picked for you on your test. Okay? So do these 3 with my notes, with watching me do it, and then try it by yourself. Do it 5 or 6 times on your own, these 3, and one of them will be very close, if not exactly the one that's on the test. Okay? I may change a number here and there, but it's doable by the same technique. So make sure any of the techniques that you needed in these 3 will be the ones you need on the test. Okay? Done. Partial fractions.